Okay.
Okay, so welcome everyone to our second Digital Future Young presentation on computational design. My name is Marina Rodriguez-Neves, and I'm a member of Digital Future Young Committee. Computational design is part of a series of presentations that we already had, and they will be available on our Digital Future World YouTube channel. These events give a chance to young academics to present research, each 12 minutes long, and then we will open to questions and we will see how long the event will naturally take. I'm very grateful to be here with Neil Leach. Hello, Neil, whom I deeply admire. Not only because of his books and lecture, also because he has been instigating this platform, which I consider the beginning of something bigger that will inspire your generation of thinkers. So especially I would like to thank to the Digital Future Young Committee for letting me be part of this and share this experience with all the members that were super smart and generous. And thanks to Virginia Melnick, Bayana Bogosian, who are part of the invisible machine that is working every day and every time. And okay, more than anything, I'm delighted to introduce the young researchers that we have today. They are from different countries all over the world, and as far as I can see, your contribution to this platform give us the opportunity to create new bonds between different universities with a spirit of solidarity. So, okay, I would like to encourage the audience, to our global community, to leave your comments or questions in our Bilibili and YouTube chat for a final dialogue that will follow the presentations. And we also have a platform to interact on Discord that we would like you to join us. So we have 6 presentations today. First presentations is going to be Dan Liang, from the Bartlett Schools of Architecture. The name of the presentation is the structural sleep. So if you want to share your screen, maybe you can introduce your work and yourself. Thanks.
Yeah, can you guys see my screen?
Yeah, we can see it.
Okay. Okay, hello everyone. I'm Dan Liang, and I graduated from the Bartlett School of Architecture, and I'm now working as an architect for now. And I'm gonna quickly introduce my year-long research. Okay, sorry. So basically, we were a group from the material lab at the Bartlett School of Architecture, and we mainly studied clay, which is a beautiful, informative, and natural material. So as we all know in the architecture field, there are basically 2 ways of using clay. One is non-structured clay, like the tiles hanging on the metal structure. Another one is structured clay, like bricks overlapping with each other. We think the structured clay is more interesting since the contact between the components should take the structural stability into consideration, which is sometimes considered limiting, but it actually follows spectacular potential. So in the year-long research, we tackled the topic of structural ceramic with wide-ranging of making, from the robotic 3D printing to traditional slip casting, in order to realize a more organic porous pattern by using special clay components. So why we choose porosity to be our main design proposal is actually porosity pattern is not only an interesting pattern, but also it's very functional. It could has mean 2 basic functions. For example, it can cool down the temperature and let the light go through to create a special visual lighting effects. So in our initial research, in our computational part, we started to generate our algorithm from the random growth of discrete components. Then we developed it into the reduce of the kind of volume from the overall geometry by the shortest paths. And then we add new algorithm like matching cube to generate an infinite porous pattern. So we call this design methodology to be designing from scratch, which means by simply place our slider, we can have infinite porous pattern. Then in order to create different levels of porosity, we started to doing research how we can create porosity in one single module. Like you can see the diagrams from here, we try to create a more considerable porosity by simply reduce the volume in each component. Then we choose the most potential geometry here. As you can see, it could create the overall shape to be like this. But actually, it looks not very reasonable because in this stage, we didn't take the structure stability into consideration. So then we started to study from the traditional masonry. As you can see here, we changed our grade from the 19 degree to 45 degree. That's a component to interlock with each other. So from the structure simulation, you can see from here, the 45 degree behaves much better than this one, the vertical one. So then we started to add a new algorithm here. The configuration of the wall with its porosity pattern is determined by the different placement of the modules. This collection of the modules is decided and optimized by the parametric control millipede, which means it will choose the most appropriate of the 6 different rotations to the particular position on this wall. So as you can see, the left diagram is before the algorithm, before we optimize the algorithm, the random collection of all the 6 different rotations. The structure behavior doesn't seem very good, but after optimization of the scripts, it behaves much better than before. So as you can see from here, which means when we define the volume, I mean the length and the height of the wall, and we decide where is the holes, and the script will automatically generate the overall shape, which based on the most appropriate structure stability. So then we have our final wall to be like this, and we wanted to bring it into reality. So then we started to do our fabrication research. So as you can see from here, we tackled 3 different techniques, including robotic 3D printing, slip casting, and also the most traditional way, compression. So according to our research, the most accurate fabrication method is actually slip casting. So firstly we use the traditional way to make the mold, and then we cast in the slip, and we got the hollow components with 4 pieces to form one single module. And then we do our design development. Like here, we use a smaller module to support the openings and to have a more multi-level porosity here. And we also tried some glazing tests here. And we designed also the patterns to create more continuity on the surface of the overall shape here, as you can see more detailed here. And in our preliminary fabrication studies, we find that if we have 4 pieces into one single component, it will cause inaccuracy. So we decided to use only 1 piece to fabricate our geometry here. And you can see from here for our joints, we proposed an interlocking system by wooden pegs, which will give the whole system more like flexibility. If our component is not that accurate, it still could like fit in. So we will have one fixed joint and one sliding joint. Our component will slide from one side here to interlock with the other components. But actually, because of the different, the variety of the pattern and also the joints, we actually have lots of different geometry here. And we started a sample wall here, which has 105 modules. But actually, we find that we have 51 different geometry, which means that it's not good for mass production. So, but in order to solve that problem, we developed a smart mold system here. As you can see, the internal, because all level geometry is actually the same, so the internal pieces of the mold is always remain the same, and the outside pieces we could give it flexibility to change to create different joints and also pattern. And we also invent a new way to fabricate our molds, which means we will fabricate the mold for the mold. So as you can see here, our workflow from CNC stage to fabricate molds for molds, and then plaster molds and sleeve casting to the fairing. So it's a whole workflow. And in order to fabricate the molds, we also studied the key system here in order to make sure our molds will perfectly interlocking with each other. And this is all our sets of molds for molds, to fabricate molds, a bit complicated. And also for the joints here, for some particular joints, we use some pieces of silicon to fabricate them. And here are our pieces of the plaster molds here. And here you can see all our procedure, how we fabricate each module. From the mold assembly, sleeve casting, and mold disassembly, then we have the final results of the piece. So compared with the traditional way, which we handmade made the mold, this way we could realize the mass production for the mold. Then we realize the mass production for all the geometries, all the components. We can give the singleness and uniqueness for each component in this way. And after the basic fairing, we got all the collection of our components to be like this. And after our compression test, which very surprised us that actually each component is hollow and it's light, but it could bear the load of 440 kilograms, which means it could start with each other to form one sample wall. So here you can see our test, and we also try some glazing tests to give it more color. So in the assembly procedure, from here, how we assemble each component is that we use the wooden pegs here to insert in the components, and we slide in another component on the top. So as you can see here, at the Bartlett, the big pro show, so we pre-assembled some chunks and then bring them to the Bartlett, and we will combine them together to form the final piece. Sorry. So then we removed all the supports, and we will get the final. Okay. Then we get the final sample wall to be like this. It creates a very appealing visual effect of the light changing since because of the geometry complexity. When the daylight change and the whole atmosphere in the exhibition hall get influenced by this facade, it actually kind of like our proposal. So in our final proposal, we suggest to use the privacy of the interior space to generate this kind of facade. Based on the privacy of the interior space. And for our final proposal, since we can control the thickness of each component by simply control the time of partial drying, so our final proposal is divided into the solid, brick, and the hollow ones. For those solid, self-supported solid components, it can be used as in the small scale, and it could create a generally mild wind circulation. And also you can see from here, the red color means the velocity of the wind gets higher, and it could create a mild wind circulation and also ventilation inside the room compared with the normal ventilation system. And so it could be used for some spectacular functions, for example, like the wine fermentation here, and also for some habitats in the tropical area. So imagine you can lean beside this beautiful wall to enjoy the mild wind and sunshine goes through. So for those hollow components, It could be used as architecture screen. We will let the simple geometry lead the way for more complex and organic porosity pattern. And here, the facade will then become a proper solar shading system. And for us, like in this group, for us architects, we don't want to push the material beyond, but we want to push it as far as it will go. So which means in the large scale, the clay always, as a building material, it often hybrid with other materials such as the metal or wood to be add together as a facade. So we suggesting a skyscraper scale. Maybe this system could work together with a metal frame and wooden pad to be the screen, and people can work inside it to enjoy the atmosphere. So imagine that in this building high-rise, you can the natural material ceramic will work together with nature to delight people inside. So that's my presentation, and also some just quick thing of how that is Bartlett and also how our sample work in this sample work create light that people need to use it. As you can see, in the daytime and the light is generally gradually change from one direction to another, and also all the shadows here kind of change, and the whole facade like kind of confusing and create very good mirror. So that's all my presentation. Thank you for listening. So.
Okay, thanks. That was awesome. It's a beautiful design, a beautiful work. So I can imagine that there is a lot of questions for you, but let's move on to the next presentation. Just let me say that we are going to let Discord link on the YouTube chat, so you can join us. And also we encourage everybody to let your questions in our YouTube chat or Bilibili chat. So thank you. We are going to move to the next presentation. Ziwar Al-Nouri and Bilal Baghdadi from the Universitat of Innsbruck with the design recording post-war Syria. I don't know if you can share your screen and introduce yourself, maybe with the well pronunciation of your names, maybe a little bit. Okay, thanks. Great.
Yeah, thank you.
Thank you.
Thank you to all guests to attending this Digital Future World for this great event. My name is Ziwar Nouri. I'm the Chief Executive Officer of Reparametric Studio and PhD candidate at University of Innsbruck. And together with my partner and co-founder Bilal Baghdadi, we will talk about our research recording post-war Syria. I would just like to start briefly, short introduction about Reparametric Studio and our self-flow and introduction about our activity with this research. Reparametric Studio is a global research with establishment in 4 countries, Syria, Lebanon, and Austria, and China. And our global vision is to introduce state-of-the-art technology in the architectural discipline. These are our partner. We are came from the common background. We were part of the famous studio of Zaha Hadid and Patrick Schumacher in Vienna. With the help of advanced parametric design and enhancement and rapid prototyping technology, the studio establishment and integrated articulated design methodology aim to improve rapid development and coexisting in the new era technology. Based on the design principle, the studio dedicated to solve side effect and problem caused by the constantly change of the world. Our core competence lay in the field of artificial intelligence and the smart city, and we are one of the first company to apply 3D scanning and the AI driven data analytic methodology for the post-war smart city development of Damascus, Syria. Recently, we have organized and co-hosted multiple international workshop, conferences, and exhibition in Europe, Middle East, and China, and establishing interconnected global network of renowned architecture company and international academic institutions such as the Angevante University of Applied Art of Vienna and like Hamburg University and University of Innsbruck and Damascus University. And one of the highlight was also like in 2019, like the Shenzhen Biennale, we invited by Carlo Ratti Associati, we showcased 2 years worth of the research and development over the post-war smart city redevelopment of Damascus, Syria. We brought the past, present, and the future of this city right in the front of our Chinese audience through the sophisticated 360-degree projection mapping. And that's like some photo. So I mean, like starting, I mean, like with the research, with the current global crisis and the urban growth rate, the world is facing growing challenge to reshape the future of city. In some cases, there are no proper guidelines for the planning and rebuilding processes. But in our team, we know that we have a major wide horizon, unifying mind and working hand, local community and advanced technology to engender significant intervention. So I mean, like the first question, which is bringing to us, I mean, to our mind, do city rebuild exactly as they were, or they are used as disaster as an opportunity to reinvent themselves? I mean, the answer was because I mean, the effect of war widely spread and can be long-term or short-term would be include mass destruction of the city and have long-lasting effect on a country, economy, and important indirect negative consequence, infrastructure, public health provision, and the social order. There is one of the reasons why more companies emerge in the field of the smart city and smart infrastructure. The problem in this field, however, is the lack of strategic planning, or more specifically, there is no strategic direction and methodology of how to plan a smart city infrastructure, taking into account all the aspects of the existing socio-economic and the infrastructure data of the targeted area. During to the recovery phase of the post-war city in Syria, the formation of the community environment and the infrastructure is already precise, and the new challenges are affecting like human existence, such as the COVID-19 crisis. The paradox here is the regenerating the future of post-war disaster city. But still with all that, we have this hope. I mean, we have the smile like from this disaster. For that reason, I mean, like Reparametric Studio answered by giving more transparent image of innovating a new methodology to regenerate the post-war smart city and involving the local community in rebuilding processes. The word of Reparametrize encloses our vision to regenerate the post-disaster city into the most advanced urban environment on Earth. The important fact here, it's the word does not mean rebuild or redevelop. We are not simply bringing back the lifeless structure and shelter back to life, because I mean, like we have the reconstruction, rehabilitation, rebuilding, and that's, I mean, the main things. But actually, the main question, I mean, like how, I mean, like if we rebuild this city, I mean, like it's without like taking care of the need the people, and that's actually the result. I mean, what we see, I mean, then what according to what the people they need, they will do. So the second main question for us, it was, can algorithm design building, or how will this data help us to regenerate our future city, or let's say recoding the data? Recoding the data by using the high technology and the manufacturer, recoding the building and recoding the community, being able to detect and analyze various parameters, considering numbers, analytic of the city database, such as area, coordinator, demography, history of civilization, detecting the destruction percentage in the city of Syria, giving a global statistic overview of the country before and after war. The data of immigration, density, resources, service, statistic of the infrastructure. This data, I mean, like actually, which we are working on it, and that's what we are doing, like building a platform so we can share it, this thought with all the people. As also we are analyzing the physical structure, their condition, and the operational capacity by 3D scanning and the social and economic analytic data using advanced AI technology to accurately analyze the large social and structural data volume, and upgrade the existing infrastructure into smart grid where multiple system tools, app platforms, social media can communicate automatically and seamlessly through the AI, promoting to help the other city, not just Damascus, developer at the other institution with their new smart city or urban development project, and using point cloud technology to map the future of post-war smart sustainable city, as well as emotional human behavior and expectation, change in need, what they want. We are able to generate the city in a smarter way, not only like by clever infrastructure, but also through the re-establishment of the human interaction. To refine our ongoing methodology, we have designed and visualized post-design and post-disaster development projects such as Zamalka into the Future, house recoding, like a smart building, focusing on analyzing the damaged fabric of the affected cities through 3D scanning technology to envision a new ecosystem for post-disaster city. This project practiced and were nominated for methodology and data analytics through AI and smart technology. We're taking a street in Zamalka. This is the area which we have it like a Zamalka. It was a town like it destroyed, semi-destroyed in the area. And we take it as a case study. So like this project was include a renovation of six existing buildings and an intervention of 2 destroyed buildings, envisioning a sustainable, inclusive, and a beautiful city that's addressed through urban regeneration by focusing on the new vision of public space. We did like a 3D scanning for this street, and then like we optimize it like by applying a new system on this building, like that could be like as a smart system, could be adapted everywhere and working with this system. So I mean, like our goal, like to apply this for, it was a new methodology for the future of post-war smart city. We have the second project, it was like a recoding smart building. Let's do that.
Okay. The features of the recoding and the principles of the recoding research was applied in this project, in these competitions, and we called about this project Recoding Smart Buildings. So the key design is an intervention of for destructed existing 4-story building in the suburban area of Damascus, Syria, and we 3D scanning the buildings to evaluate the destruction in the buildings by extract the beam model using point-to-cloud technology and to make structural analysis for existing buildings. We also inspire our concept from the traditional Damascus house, the pattern, the orientation, positions, the wind flow or airflow, also the separation between the rooms and flats, and also the courtyard and lightings. All these ecological principles we were inspired by the traditional house. So by insert of a vibrant central garden and courtyard with Ketro LVL laminated veneer lumber, forming a full integrated system by adding the screen component in the fairly damaged building elements such as slabs, columns, and elevations, while maintaining the elements which are in good status. With the benefits of today's smart global technology, used to visualize the future of post-disaster smart cities. So, developing passive traditional system into a new smart ecological system by creating a vertical courtyard, as you see, in the form of overlapping LVL slabs that have different levels of privacy, social private slabs that achieve a new vision of coding or co-living, giving copious amenities for residents, including public, green areas, vegetable gardens. So all interior living spaces are oriented around this courtyard, which facilitates a strong virtual access while maintaining an essential part of privacy. So each of these generous garden terraces provides the 5 apartments with natural ventilation, energy production, and recycling sources. They reassemble the heart of these apartments. And as we said about the Ketro LVL, with the benefits of Ketro LVL long span, these slabs are placed on a massive LVL tree-shaped L system, which has self-efficiency system of water pipes for rain harvesting, heating and cooling air pipes, and cables for smart isolation and sensors, all linked to one network that collects, automate the analyzed building data. So in addition, on of Ketro LVL would measure properties of is reducing CO2 footprint, and with the generally terraces, we have this perfect combination that adds a great ecological value. It's like a breathing lung for the whole buildings. This smart tree with its slabs has a beneficial role on the economical aspects, such as some of these slabs are designed for vegetation purpose so that the inhabitant can plant their own needs for fresh vegetables, making their small investments by selling these vegetables in the building's ground floor stores and separating a new local trading to the neighborhoods. So another application for our recording research, this called the house recording, this competition that we have entered. So through this project, House Recoding Reparametric Studio is giving more transparent image of innovating a new methodology to regenerate the post-war smart cities by using reunion ways integrated of ordinary rebuilding practice. The approach is to create high-performance urgent solutions for housing by using smart technologies to achieve a production line of prefabricated units for direct on-site installation. This strategy can in turn achieve the new form of post-war smart cities building by the hands of local citizens, reflecting their social background and their privacy. So the house unit, as you see here, the house unit is designed to use everywhere worldwide and in every climate, affordable and easy to install. It's a self-efficient working system as it generates power through turbines and can form also an integrated system when connecting units together. The aim is to use smart system to decrease bad emissions on the environment, securing low CO2 emissions, recycling a zero waste impact, and creating double layers world that can give a different use inside and outside the house, and it can form multiple functions by the dynamic design with involve movable panels and expanded furniture. Also copying with the current post-war situation and the global crisis, the unit can be adaptive on the deformation of the existing destructed buildings as it fills the gaps and works to revive the buildings. By using the still working circulation course to create levels, house recording is designed especially for limited income students, homeless families, and also everyone who wants to new hope for convenient lifestyle, especially after COVID-19 crisis, which imposed social distancing and decreased social communications also. It's aimed to make simple to anyone to design, manufacture, and assemble their own houses that corresponds to their needs. By giving inhabitants also the full integration about the site and to give them the free to use and for example, and also we focusing on the materials, the traditional materials. We also aim in our research to use the traditional materials at the clay, the basalt stones, and mix it with the rubbles to make a traditional buildings, mixing with the high-tech materials such as acrylic or epoxies, and to regenerate a material that can be used for the rebuilding the cities. Also can be executed by a high-tech or low-tech technology, such as we can use the local hands of the community, and also can we be used or executed by the high-tech such as robotics and also the 3D scanning. So.
Yes, I mean, like in the end, also our vision of course, I mean, like it's going beyond to the redevelopment of this city of Damascus, and we are looking also to be the next leader in the post-disaster urban redevelopment, offering a priority state-of-the-art technological solution for the smarter and more connected city. I mean, like especially, I mean, like we are not like aim to make like, especially like there is a lot of people asking how we can use this technique or how we can use this high technology in post-war disaster city, like with low economical. For that reason, that's the big challenge for us. I mean, like to keep the existing building, to keep the infrastructure, to keep everything that's existing, and like to regenerate the community, regenerate this infrastructure by applying a lot of rules, applying this highest technology, like with giving us a cost efficiency and like high efficiency building, and for the future, like to let the people come back, I mean, to their city. Thank you very much.
Okay, great, thanks. That was awesome. Incredible work, incredible work. So let's move on to the second presentation. Sara Codarin from Lawrence Technological University, College of Architecture and Design. She's going to present digital workflows for the conservation of cultural heritage. Are you ready, Sara, to share your screen? Okay, great. Thanks. You are muted, Sara.
Here we go.
Okay, thanks, great.
So thank you all for having me presenting today. Thank you for this opportunity to share my work. Yes, again, I'm Sara Codarin. I'm currently based in Italy, and I recently obtained my PhD from the University of Ferrara with a specialization in robotic manufacturing for the conservation of cultural heritage. And I'm currently teaching remotely at Lawrence Technological University in the Detroit area, Michigan. So I would like to start today with a bit of context at a large scale. And I think that we all agree that now we are in the fourth industrial revolution, which is a social technical change that comes from manufacturing. It opens a lot of unexplored possibilities for design at all scales, especially through new tools available, interconnected tools and new means of production that are able to connect directly the virtual with the physical world. And despite the opportunities brought by this current advanced framework, rapid technological development is not always followed by the same rate of acceptance. So this means that it's hard for an organization to absorb change. This is explained here with the MARTEC law that I elaborated, adding that if it's hard for the construction industry to accept change, it's even harder for the conservation sector, which is not technologically driven and which is strongly linked to the work of craft people on site that, for the realization of projects, interrupt the digital continuum of the workflows. And I wanted to specify that the conservation building site is a very specific context that requires specific and non-standard solutions. And when I was looking at possibilities for connecting advanced tools and conservation, I started tracking some ongoing trends that I consider relevant for the things that I'm talking about. And an important trend involving tools is happening right now in manufacturing. And manufacturing is a sector from which architects have always been absorbing innovation from. And so this trend explains that now the cost of labor is constantly increasing while the cost of automation is dropping. And I put this in parallel with the historical cost of computer storage that dropped over time and that affected also the cost of hardware. So these trends are happening in construction too. And one of the reasons is that after the recession of 2008, a large amount of workers left construction jobs and never to return in the sector. And today it's hard because workers tend to avoid construction jobs because they are perceived as dangerous, as humble and dirty. And so the direct consequence of this trend is a lack of workers and a lack of skilled craftspeople, skilled workers. So before getting into my research, I'm sharing one precedent that best support my case in terms of robotics and heritage integration. And I think that the Digital Future crew is familiar with the construction of the Sagrada Familia. Mark Burry talks a lot about this. And that's like the construction of this monument can be considered the first high-profile conservation instance that confronted design, time, labor, and materials. And these are all things that I'm interested in understanding in this kind of process. This is a very unique process, like one of the unique, it's unique in the world. But what I advocate for instead is a widespread adoption of this kind of technologies, application, and mindset too. So the Sagrada Familia allows me to talk about the notion of craftsmanship and how it evolved over centuries. And today, specifically, digital fabrication is compressing the separation between design and making, and by connecting instantly digital data and material production. And so robots, 3D printers can make this happen, can make this compression, this convergence happening. So at this point, I decided to converge my knowledge into an experiment. And I had the ambition of operating on site as a master builder. I wanted to try at least to simulate the difficulties that might occur in the conservation site, deriving from like integrating machines on site. So as long as the digital world is perfect, it's not messy, I wanted to work with more geometrical constraints. I wanted to work with irregular surfaces. And among digital fabrication methods, I decided to use additive manufacturing as an explicit connection between physical and digital. So for a full academic year, I had the possibility to carry out my research at Lawrence Tech University in Detroit, Michigan, where I found my test bed. And it is a beautiful abandoned church in Detroit downtown, built in 1911. It's registered as National Landmark. And to me, going to Detroit was a crucial location, not only for its specific conditions of consistent abandoned heritage, but also because it's one of the cities with the highest concentration of robots in the world. And the culture of manufacturing is part of the local heritage. And I think there is something amazing. And being at Lawrence Tech made me aware of how this culture is being spread. And for instance, the robot that I used, they were provided by Ballard International, which is a company that takes used robots from the automotive industry and resells them. So used robots have a second life in schools, in academia, and research. And this is a great idea. There is a democratization embedded in this process. And so with our research group at Lawrence Tech, we did the geometric survey of the building. We obtained a point cloud that I used to create a mock-up of a wall gap that I decided to be my case that I wanted to investigate, the case of damage that I wanted to study. Of course, my idea was to use robots on site to understand them, but I had to carry out this experiment in a fab lab of the school because of budget limits and because I didn't have any previous exposure on robotic fabrication. So I needed to learn some of these steps of the workflow in a low-risk environment. So I built some skills in robot programming by understanding how algorithms work and how they help managing robot motion, toolpath, virtual simulations, and predictions of collisions. And I decided to use raw clay as my base material because not only because it's cheap and reusable, but because it allowed me iterations. And I needed a lot of flexibility during this process. So at this point, I created this close relationship between the physical and the digital world by creating a digital twin from which I could learn and fix mistakes before dealing with materiality. And I consider this an extension of my working space, but I consider this also a relationship. I could create this relationship between time and space. So the outcome of the workflow is the result of different extrusion sessions. It is a very specific application on a technological unit that I refer as a proof of concept informed by advanced ways of making. And so this realization allowed me to speculate also on how to advance the experiment eventually, how to think about follow-up, and how to optimize and get a more sophisticated outcome. So the process validation resulted in a MVP that means a minimum viable process. So what it means is that not only the outcome, but the whole workflow was a prototype to me. And so I structured the work that I've done to compare like my initial hypothesis, the actual experiment that I carried out. And I looked ahead on future scenarios based on my acquired knowledge. And to me, the proof of concept of the wall gap, which is a very small unit, is a starting point for a much broader application. And the systematization of the workflows allow me to identify the skills needed to carry out the working methodology. And these skills overlap at various phases, and I imagine them to be fully integrated in a future scenario. And so what I want to say with this is that architects stand to potentially become in the future the prime operators of the fourth industrial revolution, because they will be able to manage digital complexity. And so I think that higher education plays a fundamental role in the context of the fourth industrial revolution. And for instance, when I was at Lawrence Tech, I had the possibility to teach a robotic fabrication class with students without any previous experience in using robotics. And the students, in like only one semester, they were able to work for the realization of speculative models by translating ideas into reality using a robot. And they took advantage of the potential of robotics to iterate their design processes. And I considered the class that I taught a second experiment, because I was imagining in the future of construction, the fact that the downstream phases of making architecture could be populated by robots, like in the next future, hopefully. And this is also an approach to train the future master builders. So what's the issue though? To advance research, we need more capacity for people to be using robotics. And so with this purpose, I'm currently involved in the creation of a nonprofit Fab Lab in Detroit for the built environment, which is called Citizen Robotics. And this Fab Lab will provide access to robots and training with the aim of upskilling the construction workforce of the future. And to get to the conclusions, I think that some practical experience is needed in robot construction before dealing with heritage. And if I read, for instance, statistics in Europe, I see that buildings are old and the investments in new constructions are dropping. And so there's an opportunity in the next future to work on existing buildings, for instance, for refurbishment, for deep renovation. It's a nice training framework. And then I think there's an opportunity to build knowledge and to shift to dealing with heritage. And with the idea of developing first-hand knowledge in construction robotics, I'm also a member of a startup called the Mod Public that operates in Detroit too. And it aims to make affordable houses through the use of robotic construction. So the starting point is a very small unit, which is like a small house to start to learn from the process, the robotic construction process. And that's here, the last thing that I'm sharing, some early stage ideas. It's a bit early to share them, but I'm super excited about this, and I hope to see them a year from now in reality. And so this is a study, some early stage ideas for the development of a building cluster in Detroit downtown, driven by the idea of using additive manufacturing in some parts of the construction process. And as a designer, I'm using this opportunity to investigate the potential of robotics to deploy mass customization with a case-by-case approach. And this ties back to the understanding of what conservation means to me, because this is a nice way to think about conservation in terms of like urban scale, in terms of neighborhoods, and I'm using like my state of mind and my knowledge to apply that to build knowledge for new constructions too. And I would like to thank you for your attention, and thank you very much, and I hope you enjoyed it.
Thank you, Sara. It was sophisticated research. It was so great. So, okay, let's just say that our audience community can let your questions in our Bilibili chat and our YouTube chat. And on Discourse, of course, that we'll let the link there. So we need to move on to the next presentation. Okay, there is Omar Fabrisio Avellaneda Lopez. He's a researcher from SMiA group from Polytechnic University of Catalonia. And he's going to present parametric design of deployable structure movement. So if you are able to share your screen, you can start now.
Okay, thank you. So sorry. Okay, perfect. Okay, thank you, Marina, for your introduction. Okay, I am PhD from Polytechnic University of Catalonia, of course, and how you say, and I am researcher in SMiA research group in structural morphology and architectural, and my research focus in transformable architectural, computational design, and advanced geometry. And today I am talking about my part of my research, my PhD research. It's about parametric design of deployable structure, controlling the movement of the system. So everybody knows the very great legacy. Sorry, let me check. My camera is take off or take on, I don't know. Okay, perfect, sorry. So everybody knows, how I say, everybody knows the great legacy about these designers and inventors like Buckminster Fuller, Emilio Pérez Piñeros, and Félix Escrit Pajares. So, but currently have other researchers that focuses in deployable structure, but focuses with using the parametric design or computational design for create a new configuration for this structure. For example, Charis Gantes, his new adaptive structural mechanisms, or Niels Stederman when using the parametric design for create a new configuration with the deployable structures. And in the final case, for example, Kelvin Roberts and Niels Stederman, who talking about the digital design of deployable scissor grid based on circle packing. Exactly in this point, start my research. So I focuses in this part of my research in deployable structure with articulate straight bars. I don't know talking about the angulate bars in this part of my research. So my first step in this research is try to explore in a geometric things about the deployable structure and motion design exactly. So for this reason, I start to create different algorithms focuses in the motion design for this structure. In this case, you can see the symmetrical axial systems. And the second one, you see a asymmetrical axial system, but with a straight movement. And finally, everybody knows the asymmetrical axial system with the curvature motion or curvature movement. So the next step with this exploration with parametric design is using try to design the one model. In this case, it's a square model or the symmetric biaxial system, but it's possible to create the triangular module or the hexagonal module too. And sometimes we can try to define a special parametric design of the deployable structure. In this case, asymmetrical biaxial systems. And finally, I focuses to find one algorithms with I can apply architectural spaces, of course, with a space application in architectural. In this case, it's asymmetrical axial systems. So with the more complex geometry, I try to find the different application with the different architectural applications. Sorry. I can domain, I can define the movement, I can define the number of the archers, I can define the number of the models, and we can define, of course, the dimensions. And finally, I can define with these algorithms the angles on incidence with this structure. And in every algorithm is part of these parameters. This is the basic parameters to control for this structure. So in this, follow these parameters, I define the different geometry, the difference apply with the type of surfaces. In this case, it's a synclastic surface with a symmetrical biaxial system, but it's possible to apply the asymmetrical triaxial systems. In this case, it's a hexagonal model and in the same shape with the synclastic or synclastic surface or sphere. Then we exploring more complex geometry, in this case, anticlastic surface with double curvature in different directions with the square model, and I create a asymmetrical biaxial system. It's a hyper shape. And finally, I try to design with architectural elements, in this case, arches. I try to design a different configuration with space application in architectural, of course. And finally, you can see here a donut geometry, donut shape, and we can exploring the different n arches with different geometries and more complex movement in these designs. So exactly after this analysis, after this geometric analysis, I propose one classification focuses in these two different types. For one way, the motion vectors. In this case, we have the axial vectors, biaxial vectors, triaxial vectors. We have here the special configuration with the prisms and solids. But for other way, we can create the straight deployable system, or with the different shape, like a monoclastic surface, synclastic surface, anticlastic surface, or finally with a special surface with the more complex deployable structure. So after this exploration, geometric exploration, the next question in my research was who we are control the movement of this structure, because normally this structure have three positions: the open position, the deployment position, and closed position. So the deployable structure have 1 degree of freedom. So I designed one algorithm using grasshopper and kangaroo for controlling the movement of this system. So what is exactly in this algorithms? So I insert one tension element, in this case one cable, and using dynamic relaxation, it's possible to control the final position for this system. So in this case, we can with this algorithm we can have the real simulation, and we can calculate the different elements and different dimension and exactly dimension for the final prototype. So the next step for my research was apply exactly this concept in the asymmetrical system. So I applied this asymmetrical system, but if I don't put this cable, the structure collapses. So in the second one, we can see here, I insert the cable and I insert this algorithm, I apply the forces, and then I can control the final position for my deployable structure, my deployable system. So with the next step in my research, I apply the more complex structure. I using one arches with hexagonal modules, and I apply this algorithm in each hexagonal models. So finally, I can control the final position of these arches, of course. And the more important thing is that I have the real simulation with this structure before to build the prototype, so the small prototype or the real full-scale prototype. So when I have this all geometry and analysis exploration for the controlling the movement of the system, the next step in my research is design the mechanical movement testing using SolidWorks and apply virtually testing. Is very simple, a simple stress and deformation analysis for the 3 different models. In this case, in the first one is a square model, in the second one the triangular model, and finally the hexagonal model. So when I have all this information with this parametric analysis, the next step, of course, is start to create the small prototyping using laser cutting or 3D printing. So this in my research, I try to build and to use the different materials before to these final prototypes, small prototypes, and finally I try to find very good material, because we can explore in wood's material, for example, or different other, in this case is PLA material. And the other point is try to design the tile construction for these brake elements to stop the movement for this structure. So after this parametric analysis, I try to create one methodology for parametric design of deployable structure. The first step is the form finding, or choose the surface. Sorry, and then the parametric design using different algorithms. Finally, using the controlling the movement of the system, this algorithm for create exactly what is the final position for the systems, and finally make to the tension and information analysis for have very good information for begin to create the small prototypes or the full prototypes. So in this opportunity, I show you one case of study. Is a vertex pavilion using 378 bars, 216 PVC points, and more or less is a 90 meter squares built for this structure. So I choose the triangle model because it's used more with this with triangle more used less elements to build the arches. I start first the geometry, and I testing the geometry first, and then when I have this very good testing with the movement, I apply the controlling the movement of system, these algorithms for controlling the movement of system. I insert 2 cables for create this in real-time simulation and have the final geometry and the final dimension for my prototype. So with the next step is start to create the small models. In this case, I testing with the plywood bars, I testing with the 3D printing in PLA, and finally I create one small model using laser cutting with metacrylated bars and 3D printing with PLA joints. So I define the final geometry for my case of study. I define the central core with joining the 3 arches in the triangular shape in the floor, and then I create and then I testing these groupings to the arches, this shape, and I using Grasshopper and Millipede for try to have the different tension stresses and deformation analysis. For with this result I have exactly what material is better to use for build the prototype. So the next step is ensembling test. The first step was the first test was the 1 arches. I apply exactly dimension to the algorithms, and with testing, and the first impression is that it works, and the next step is try to create this grouping for 3 arches, and testing in real time exactly what happened with this structure and what is the structural behavior or mechanical behavior with the joints, with the bars or the PVC point, joints. So you can see here the different construction details. You can see here the brake elements to stop the movement in this part, using rigid element to stop the movement. This one is the PVC pipe low cost build, low cost detailed construction with these arches. Finally, with the help of the architectural students for Tecnológico Monterrey in Mexico, we have the opportunity to build this very fantastic structure. The first step was create this core with the three arches, a grouping with 3 arches, and then grow up to the external arches. And finally, we put the membrane textile. In this case, was lycra. Finally, I want to show you this short video. I want to show you this small video when you can see here a little package for the whole process. The first part, of course, is all this parametric analysis, and then with this information we can build with more exactly dimension the every arches and every distance from the arches, and create the vertex pavilion. Finally, this experience was very great for this research, because we can show the different problems when we can test in the forces of the wind. We can test in the different mechanical behavior for the joints, and this was the first step to create the new new multiple joints. Sorry. Oh, sorry. And finally, this is some picture about this project. And who I say before, this project was very interesting, because with this big prototype, we can find exactly other problems when you build the small prototype, you don't see this problem. In this case, it was very great. And well, of course, finally, the discussion and conclusion for one part is the parametric design methodology for the deployable structure is very great, because it's even it's the low cost prototype manufacturing, but it's very speed and speed and times is very important with this structure, because with the parametric design we can build more fast and have in less time the build with this structure. The scale change and construction detail is very important when you build a real prototype. I believe that this structure need more diffusion and application in conventional architecture, because I am sure that this structure had very opportunity to in conventional architecture. So, and the future hits, I try to start with the algorithm library. I have more than 100 algorithms. So I try to develop a plugin or parametric tools within Grasshopper environment or difference. But I try to create this parametric tool. The other idea is try to incorporate electronic actuators to control movement electronically. Of course, you see here one case of a study with low cost material, but I have the idea to try to build and manufacture the high quality material prototype, the 1:1 scale, using materials and manufacturing techniques. And I believe that this structure had really a specific application for emergency architectural. Finally, this imagine I tried to recreate this application with emergency architectural. So I believe that is very interesting exploring this part. Thank you so much for this opportunity to share part of my research. If you want to know more information, you can visit our webpage or Instagram account. Thank you so much.
Okay, thank you, Omar. Gracias, Omar.
Thank you, Mariana. Gracias.
Okay, so that was a super clear process and didactic presentation. So now let's move on to the next one, who is Angelica Videla and Gonzalo Muñoz from the Universitat de Chile. And the presentation name is Results from Educational Experience, Exploring Computational Design Remotely. So if you are able, Angelica, to share your screen, thank you.
Can you see the screen properly?
Yeah, perfect.
Okay, great, perfect. Hello, everyone. My name is Angelica Videla. And first of all, I would like to thank DigitalFUTURES for this opportunity to present our ongoing research to such a global community. Our presentation today is called Results from an Educational Experience, Exploring Computational Design Remotely. And it is taken from the specialization course of Advanced Digital Design in Complex Geometries at the University of Chile. I would also like to present ourselves briefly. My colleague Gonzalo Muñoz is an architect and the tutor assistant of the Design Studio 6 and of the specialization course of Advanced Digital Design. His research is focused on self-structured geometries based on computer design processes. My name is Angelica Videla, and I'm an architect and an assistant professor at the University of Chile, where I direct the Design Studio 6 and the specialization course of Advanced Digital Design in Complex Geometries. My ongoing research is focused on computational design with a specific interest in structural geometries that are optimized for digital fabrication, 3D printing, and robotic fabrication. Trying to push forward our research as much as we can, we will also be teaching at the Acadia conference this year with a workshop called Architectural Geometry and Morphing Patterns. If you are interested, you are more than welcome to join us in October. Starting with our presentation, and to give you a little of context, we would like to start mentioning that this crisis has been an opportunity to first improvise a virtual community between the students, the teachers, and the final jury of this course, as well as many other virtual communities around the world, creating a massive ecosystem benefit from the digital transformation of our era. And second, a chance to learn and experiment at a distance, a rapid retooling to address the new possibilities of what architecture could be through computational design. More specifically, in this new virtual education experience, the students explore how to design with an efficient procedural polygon modeling methodology with Maya. This is a process that breaks down a complicated task into discrete modeling operations. In addition to procedural polygon modeling, the students also explored how to integrate topological patterns into the low poly modeling workflow through morphing patterns. The ambition of this methodology was to develop formal and aesthetic qualities and that are not indifferent to their processes. Each one of the students explored his own geometrical sequence and create his own set of rules in that sequence. Of course, this methodology is not new. It has been well spread among the computational design, academic, and professional community. But in a way, it was a new way to address creative process here in South America because of the slower digital transformation of our industry. The skills that were explored in this course include subdivided surfaces, low poly geometry components, and organizational logic, sculptural mesh modeling, and discrete modeling operations. To test our design approach, we use primitive geometries as the playground for this design investigation. To exemplify this, we would like to present 3 case studies from our first semester of this course, a course that was carried out entirely online. The first case study is Copali by Angela Rodriguez. Angela developed a procedural polygon sequence that started with a primitive geometry, in this case, a surface. From her original surface, she extruded several faces to create columns, subdivided them, and then bridged them together, creating a branch structure that generated partitions and supported the canopy. An interesting part of her creative process was how she developed almost all of her digital model upside down to better visualize the branching and the bridges strategies and to achieve the curvature of the canopy by using physical forces in Maya. Angela also developed different iterations of the materiality through a combinatory process, combining 3 variables, in this case, temperature, cold to warm, reflection, gloss to matte, and opacity, opaque to transparent. Here are some of her results, as she made many iterations. And here is a short animation of one of her iterations. The second case study is Osamenta by Benito Claria. Benito developed a procedural polygon sequence that started with a primitive geometry that was also a surface. The low poly geometry was quite simple. By pulling vertices up vertically, he generated his basic shell geometry. Benito showed a strong interest in incorporating pattern in his geometry. He studied different surface grids on his high poly shell and used a morphing pattern process to be able to control the size, gradient, and density of his pattern. With his procedural sequence, he then generated a family of shells that vary in terms of size and proportion. He developed different iterations to study the relationship between the shells, how they interact, and the resultant space. Here is one of the iterations that was considered the most successful. And here you can see the results of the morphing pattern process. The last case study is La Recogida by Vanessa Soto. Vanessa's project was a little different because she started with the cylinders as a primitive geometry. She wanted to develop her geometry in a radial way. In order to do so, she started with a cylinder with 3 faces. Despite the simplicity of the model, what was interesting here was how it was modeled. By using a parent geometry and 2 instances of this geometry arranged radially, the 3 branches were all modeled simultaneously. Then, more detail was added once the main model was done, such as materiality, texture, and lighting. Here are some of the images that she produced for the final submission. I would like to say a few words on the general outcome of the course. The educational experience resulting from this course was a wide diversity of design strategies of procedural polygon modeling, organizational logic, and morphing workflow that could be applied to any architectural geometry or typology. Choosing procedural polygon modeling as the main methodology for the course was a good way to teach students discrete geometry operations, low poly modeling, and simple modeling procedures, and was also in the end a great hand-on modeling tool for the students, most of whom didn't have any previous modeling experience, to generate a wide variety of projects with highly expressive design. The fact that the course also integrated a theoretical introduction on computational thinking and incited the student to choose conceptual and aesthetic reference for the projects may also be one of the reasons the design were so diverse and personal to each of the students. In the end, teaching remotely also turned out to be particularly well fit for this course. Firstly, maybe because it was a digital course and the digital component was really emphasized by the whole process of having to work with computers. Corrections were made easier by being able to open and look at the 3D models directly with the students. The tutorials and corrections were also all recorded and posted online, so the students could consult them afterwards if they needed to. And given the challenging constraint we had of having to fit the course into a shorter semester, the modeling methodology and computational techniques proved to be simple enough for the students to absorb quickly and experiment with. What are you seeing here are a few of the final images that were presented by the students at their jury that also took place online. Moving forward, we plan on continuing work with the same methodology that work well with the format of this course. However, looking at the wide variety of designs that were produced, we can see how computational design strategies can provide numerous outcomes. In the future, we would like to focus the outcome specifically towards structural geometries by implementing structural parameters in the design process. The structural parameters will be directly related to the geometrical form and act as an evaluation test parameters that will confirm the structural viability of the geometry. This could allow us to optimize our geometry for digital fabrication, 3D printing, and robotic fabrication, and incorporate the manufacturing process and its specific challenges within the architectural system to develop by the students. Thank you all for listening to us today. We will also like to thank DigitalFUTURE again for this opportunity, and thank to our students for their work this semester.
Okay, thanks, Angelica and Gonzalo. That was amazing. I'm really glad to have you here. We have already Alberto Fernandez in the first computational design session, so really glad to have you here. Okay, we need to move on quickly to the last presentation. So it's going to be Shervin Asadi. I don't know if you're ready to share your screen. He's from TU Delft, and he's going to present a discrete generative design methodology. Are you ready, Shervin, to share your screen? Yeah.
Yes,
okay, thanks.
I am sharing.
Thanks.
Okay, hi everyone. Good day to you. My name is Shervin Asadi. I'm a researcher and an instructor at the Chair of Design Informatics in TU Delft. In the next couple of minutes, I will be presenting a discrete generative design methodology, which gives an overview of a line of research that has emerged out of several research and education projects that me and my supervisor, Dr. Nouri, has been busy with lately. So I will start with the scope and the premise of this research, and then I will outline the underlying framework based on a discrete mathematical formulation of a spatial design problem. And we present a workflow that solves the formulated problems. And finally, I will introduce a toolset that provides an open source implementation of this methodology. Well, starting from the scope, we see the design process as a chain of decisions that goes from the most abstract subjects, such as deciding on the importance of different factors in design, like light, view, noise, to configurational decisions, such as whether to have an opening between two spaces or not, down to deciding on the details and materials of the building. To give you a visual overview, here you can see some student works. Framework start top left with the contextual information that they have gathered, and then developing a spatial plan, middle top, developing agent behavior, bottom left, synthesizing configuration, middle bottom, and the final building on the right. The same process is presented in these two projects as well. You can follow them from top to bottom. And as you can see, the results of this methodology are not limited in terms of style, concept, or organization, yet you can trace back the line of reasoning through the chain of decisions in the design process, whether it is conceptual or configurational decisions. To dive a little bit deeper, our framework has three main stages, which each one of these stages incorporates different domains of mathematics, going from abstract to concrete. Starting with planning. In our framework, planning is about specifying the set of priorities based on the preferences and requirements of each space. The output of this process is two graphs that represent these preferences: external relations, environmental preferences, which specify exactly how we want these spaces be with regard to these environmental fields, which are going to be like view, light, or noise. And then the next one is internal relations, which describes how we want these spaces, their relation between each other to be. The next stage within this framework is configuring, which in this stage, we focus on generating a spatial arrangement of the spaces using a graph theoretical framework. The input, of course, is the output of the previous stage, and also a voxelated envelope, a three-dimensional discrete representation of the buildable site. And the output is going to be a labeled graph, technically matching every single voxel within this space with one of the functions that we are going to place. The last is shaping, which focuses on polygonization algorithms that takes the topological configuration that we have received from the previous stage and turned it into a geometrical image representing the building. Our proposed workflow is a structured set of methods that goes from abstract to concrete in scope and solves the problem of the discrete spatial allocation that has been formulated in our framework. In this presentation, I'm going to only focus on the methodologies offered for the configuring step. Starting from the contextual information, we take the physical definition of fields and generalize it to a data structure for contextual information, which contains sample from measured or simulated data. As an example, here, this is a distance field. And all the figures of this presentation, the redder the color, the higher the value, the bluer the color, the lower the value. Here you can see a distance field describing the distance of every single unit of this field to the points of interest, which are the white circles at the bottom of the page. The points that are closer are bluer, the points that are further are redder. We can generate a similar thing for a visibility. I have thrown in two obstacles to make it more interesting, but technically the red points have 100% visibility toward the points of interest, and the blue points have 0% visibility. We can generalize this concept of fields to 3D easily to describe, for example, the field of sunlight, how sunlight each unit would receive, or how much of the sky is visible from those voxels, or for example, how much they are obstructing the view of the neighborhood toward greenery. We can also describe internal qualities. For example, how accessible is a certain area of interest from each one of these voxels. Having all of these different fields would take us to the next step, which is multi-criteria decision analysis. And within this step, the main objective is to evaluate the value of each voxel for each program, given the preferences specified in the planning stage and given the raw contextual information that we have inherited from the previous stage. What we would do is that we would utilize fuzzy logics to first estimate the value of each voxel field for each space. What does that mean? Take the example of the distance field and imagine that we wanted the closeness, as close as possible as we can be to the points of interest. For such a preference, the value of the points or units of the space that are closer to the points of interest are highest. So the distance value field of 0% closeness is going to be something like this. But if you want to be at 20% distance, it would be like this, or 40 or 60. We can take this idea and bring it to the visibility field as well. What are the valuable voxels if we don't want to have visibility toward the points of interest? If we want 20% or 40 or 60. So you get the idea. I think that the next step is to be able to put these different fields, combine them together in a systematic and rigorous process to avoid comparing apples and oranges, because these different fields have different physical dimensionalities. So for this reason, we use a second value, which helps us to aggregate the value of voxels across the fields for each space. To give you an example, and our previous points of interest are the fireworks on the stage, and we want to position people in front of the stage so they can both see the stage, aka have the visibility, and be at a safe distance. In this case, we would value 60% visibility and also 40% closeness to the points of interest. What we need to do right now is to combine these two different fields together in a way that we are not mixing their dimensionality. So we can give 80% priority to the visibility and 20% distance, and the bottom field is going to be generated. Or we can go up to 80% importance to the distance and importance to the visibility. And this, after we have mixed, or better like put together these two different fields together, what we need to do is to actually interpret the analyzed aggregated information in the fields for each program, which we use swarm intelligence for. What we would do in this method is to implement an agent-based model that takes the fields as the environment and specify each program or each space as an agent, which in this case is benches, and then define the behaviors of these agents. In this case, agents are going to be unicellular, and they're only going to be walking around. So let's take a look at this simulation. What we did over here is that we implemented a discrete version of gradient descent. And if the video is low, yes. And what agents are doing is technically moving toward the voxel that has the highest value, and resulting in a configuration which is similar to this. But this is too simple because we had the field already, and it was obvious that the best locations, where are they? However, the problem is not trivial when the fields are not static. Imagine a situation that the festival is happening in Corona times, and every person is supposed to keep 1.5 meters away from everyone else. What we had to do to incorporate that extra information is to generate a new field, which is an agent's distance field, which this time is going to be a dynamic field, meaning that it's going to be evaluated in every iteration of the simulation. Therefore, within the new system, if we implement that this new dynamic field, what's going to happen is that our simulation is not going to be that much predictable anymore. So we can see in this new run, yes, that the field underneath the agent is being updated as the agents are going through the process. And at the end of it, they would achieve a configuration which is not as dense as the previous configuration. To take things a little bit, to make things a little bit more interesting, what we can do is that we can add more fields, but this time 3D fields, for example, accessibility, agent closeness, sky visibility, interdependent sunlight, and height. And we can also define different kind of spaces, aka agents. In this case, we would define 5 different spaces. We can also implement other kind of behaviors within our agents. For example, this time it's going to be multicellular, so they're not going to be composed of one cell anymore. Then they would be able to occupy any space, meaning that if a voxel has a high value, they would take it, and they would desert the voxels that have lower values. And also they are able to negotiate between each other, meaning that in a situation that dealing a voxel would cause the whole system to have a positive sum, they would do that. If the video loads, yeah. So as you can see in this example, the orange space, for example, wants to be as close as possible to the blue space. But the blue space doesn't care about him that much. He just cares about the sunlight and the view. That's why he goes up. Let's watch it again. Yes, great. But the orange space moved toward the blue space throughout the sides, from the left to the right, and finally end up very close to him after he figures that he doesn't actually need those initial voxels. But the thing that is really interesting over here is that we can take this to the next level and technically change some of the preferences. For example, we can increase the tendency of the blue space to be closer to the ground. So what he would do is that he wouldn't rise much. And if it was properly, the orange space would not rise as much as well. Yes. And consequently, there would be more opportunity for the gray space at the back to go higher in elevation. We can see this compared together when we put them together. Therefore, we can change the preferences of the space at the beginning of the workflow and see the effect in the final configuration. In other words, this enables us to create a bigger feedback loop, allowing the stakeholders and the designer to see the consequences of their decision about the preferences of spaces, effectively providing a control mechanism over the entire decision chain. Last but not least, I want to mention the toolset that we have been developing and the whole processes within this presentation has been made of. Topogenesis, which we started to develop it as a toolset for spatial decision-making framework. And however, it eventually grew bigger and started targeting more use cases like generative spatial design and simulations, 3D image processing, topological data analysis, and machine learning. And in its current form, it can provide a basis for connecting spatial computations with AI libraries because it uses a standardized representation of the arrays. I would like to end this presentation by giving you a summary of the contributions of this methodology and also acknowledging the research grants that made this research possible and guarantee this continuation. If you are interested, stay tuned. We are writing a few papers about this line of research. Thanks.
Okay, that was amazing. Thanks, Servin. Okay, that was our last presentation. And maybe you can stop to share your screen open to some questions. But just a first comment about the presentations. I'm really impressed about the quality and the diversity. All of you guys, all the presentations were amazing. The process were super clear. And as far as I can say, even with all this diversity, we can all say that we have a computational thought. So that we already think, all of us think in a computational way. And this is why, at least from my point of view, the presentation was so clear, because it was step by step in a didactic way. Even the educators that are here today, they were super clear in that. And I think I want to keep with something that Angelica said about different results, that they get it, because computational design finally is not about shape, or it's not about style. It's about the way how we think. And we already do it in that way. So just that comment to move on to the questions. We have a lot of questions from the audience, but maybe we can start with some comments here. The committee, the other presenters are from Neil as well. Thanks.
I mean, I can start. I think it's really interesting what you just said, Marina, because that's what I was thinking, that this is kind of interesting that all the presentations were so different, but kind of most replying to what Sara was presenting, that the theme across all presentations is kind of about computational design and how it sets up a new relationship between these dynamic systems of technology and humans. I think it was most clear in Sara's, but I think it kind of comes through in everyone's presentation. And you know, how technology is so widespread, and how we are all already kind of thinking in terms of computation, and how that kind of changes our perception as well of the built environment. And so my question would be that kind of this dynamic approach of design and towards design that works with technology kind of engages the architect and the stakeholders in a different way. And buildings are more perceived kind of over a longer span of time. And a lot of the projects that you were presenting don't have like an end point, but they're kind of like stretched out over time. And so my question to you is, how do you see the role of the architect, and kind of the change in the role, or maybe the roles of the architect in the future, as this kind of engagement with the built environment and computation as process? Maybe someone can speak to that. I mean, if not, if this is too much, I don't know.
Maybe I can pick up and maybe direct a question to some of the audience. Thanks, Victoria. I think it's a very relevant question to think about the role of architects and see how design automation and production automation can basically change the way we position ourselves in societies. I really also enjoyed the diversity of the projects, ranging from cases that we are dealing with this idea of going from physical to digital, basically breaking the chain of always going from digital to physical, all the way to the cases which we are rigorously discussing education and how we can basically transfer knowledge. And throughout the last presentation, which we are discussing systemic thinking and basically addressing how in an educational also context, but in an open source basically culture, we can provide knowledge to others. Maybe I can direct a question towards Sara, who was discussing basically the role of automation and computation and how this is going to change the way we work in the future. Maybe you can reflect on that.
Yeah, absolutely. I wanted to leave space for other people because I had specifically one slide for that. So yes, I really love talking about the concept of master builder in terms of not only a person, now I'm talking about the architect as a master builder, but of course it's like a team of people being able to manage complex workflows. That's very fascinating to me, the fact that through my experience, I noticed that I had a state of mind of thinking like sequences of actions and sequences of tasks happening, for instance, in design, but also in construction. And like thinking like in, as Marina said, like in the computational thought, like mindset, like we have a more dynamic sense of understanding design and construction. And I think that the biggest potential is to improve building quality and improve the process, because if we have a certain immediacy in achieving a result, let's say like robotics or 3D printing are translating almost like simultaneously our ideas into a material, into matter. So this allows us as designers to spend more time in the design itself, to make more iterations and to improve the quality of the outcome. I think that it's such an amazing moment to experience this process changing, and we are like the main professionals in charge of understanding these things.
Mm-hmm.
If that responds your question.
Awesome. Thank you.
Can I ask a particular question? Yeah, first of all, I wanted to kind of say that a couple of the projects were kind of showing a kind of scaling up of the operations, which I always get very nervous with, because I don't think you can quite do that. You just you can do it visually on the computer, but actually from a structural point of view, it's not quite so straightforward. I mean, when you scale up, let's say from an ant to an elephant, the elephant gets much more stocky, and there's a structural logic to that. I won't go into that now, but I did put the thing on our discussion, an article about that. But my question was for Dan. A very nice project, Dan. But at some point, you tested out the system structurally using timber, and then you shifted to clay. And it seemed like the basic model had been elaborated using a certain material assumption, and then you shifted to another material. Did I miss something there, or because clay performs in a very different way to timber? It has obviously less tensile capacity. So that's a question for Dan.
Okay, so basically we actually I think it's my presentation caused kind of misunderstanding, because actually our material lab is actually like the group of us is actually focused on clay, and we didn't try to I mean, I didn't really have the procedure starting from the timber, then clay. Actually, we are all just focus on the research about the materiality of clay. But in this procedure, and we try different fabrication methods, mainly use other materials. But actually, at the last part of my presentation, I mentioned about the clay need to hybrid with other kinds of material like metal, wood. It's because that for our component, it's really light. I mean, the stick casting components really light, and it's kind of beautiful if it could be used as small scale, or it's itself supported in a very small scale as small scale architecture. But in case of a big architecture, I mean, like a skyscraper scale, we couldn't force the clay to just it couldn't work, because it kind of due to the shrinkage based on the materiality, when you fabricate, after firing, it's not that accurate. So it has to be hybrid with other material in case of the large scale. But in small scale, it could be only work with clay itself. So in our research procedure, we try to test different kinds of material just because we need to fabricate the molds. We test how to make the molds, how to produce a more accurate component. That's why we study different materials, basically.
Just follow up question. Did you get, I mean, engineers always get fascinated by failure, right? I mean, it's not interesting if something stands up. As soon as it fails, then it tells you something about it. And there was a big conference right after 9/11 when the World Trade Center collapsed, and they were fascinated. How did that building collapse as such? So sometimes when you make presentations, you want to show how fantastic it is, how perfect it is, but sometimes the imperfections are much more interesting. The point where it collapses can be super fascinating. Did it collapse? Did any?
No.
Okay.
You mean which stage?
I mean, when you started fabricating it, did you start seeing cracks appearing and so on?
You mean when we are doing the assembly of the final wall, or?
Yes.
No. I remember an interesting thing is actually Bartlett doesn't allow us to build that wall in the exhibition hall because they're afraid of kind of afraid that it's dangerous. You know, they don't allow us. That's why we assemble the wall at the farm, our tutors, studio like. And when we are doing pre-assembling, it's kind of like a risk. We don't know how much layer we can stack on all the components on the top of each other because they are light. And there's never anyone who done something like this. Before we do the final wall, the fabrication of the final wall, we went to I remember a structure engineer, and they said it's impossible to doing something like this. But our tutor and also our teammates, we think no one can say it's impossible because no one done anything like this. So we just try to layer it one layer after another, and we say, okay, the wall can be fulfilled. But when a very interesting thing happened when we remove all the chunks, because we pre-assemble the chunks, right? We didn't pre-assemble it in a horizontal way, but we have to pre-assemble it in a vertical way because due to the gravity and also the shrinkage and accuracy of the clay components, we have to do it in this way, because if we do it in a horizontal way, it doesn't work when we combine different pieces together in a vertical way in Bartlett. So we pre-assemble it also in a vertical way, but when we remove it from the farm to the Bartlett, so at the bottom, some part, one component breaks. So we were like, okay, so we're like disappointed, but it's all okay. We find that it's an opportunity for us to replace this one component because it's a modular component. So that's also the benefit of this system. It's a modular system that when there's, for example, it's kind of sustainable. For example, if you want some parts like broken or you wanted to replace some parts, it's very simple because they're all the same. Yeah. So that's an interesting thing, I think.
Right.
If I can follow up on this operationalizing fabrication, let's say, I would like to ask like two questions. One is for Dan. You mentioned this interesting process where you used molds to do this potentially mass fabrication or mass production of modules, right? And I was wondering, unless I didn't understand correctly, these molds were for very specific components, right? So I thought that this is a mass production of a specific design. Do you think it's possible to have, for example, maybe a single set of components you can mass produce and make many different designs that perhaps even have different aesthetics or different, let's say, end goals? And my other question for Sara, just put it together, is you mentioned that you had a very nice example, a real world example, and it brought into my mind the place where I'm from, a very small island in the Cyclades, where a whole city needs restoration, essentially at the center of the city itself there. And the problem there in real life is that machinery and construction cannot really reach there. It's really difficult to even bring something there to do restoration process. So I was thinking if you have any ideas if this can be operationalized in this type of environments where you have this kind of things. Thank you.
So just to check if my understanding about the question is right. So firstly, you are asking about the modes, right? So you are asking about what I mentioned about the smart mode system. Is it possible to produce like different kinds of mode, like different kinds of geometries? No?
Yes.
Okay. So yeah, the development of the smart mode system is actually to solve the challenge to meet the requirement of challenge how we can realize mass production, because the tricky part of the modular unit is actually the geometry is all the same, but due to you know, we are playing with the tricky thing about the different rotations of one single geometry. You can think of the geometry as a bounding box of geometry is a cube actually, but each cube has 6 different surfaces. But in this way, 2 different rotations when they meet each other, the connection part is actually different. So that that will result in the connections. I mean the joints. And also, if you wanted to create more like fascinating patterns, different patterns on the surface of the component, this stuff all result in the singleness and uniqueness of each component. So actually, this smart mode, that's what I mentioned, that the inside part, 4 pieces of the smart mode is actually the same. In order to ensure the geometry, I mean all the geometry the same. So the inside part is actually to define the geometry of the final component, but the outside are smart pieces, which means you can always swap. Because the time of the presentation is limited, I didn't give a really, you know, like a very specific explanation of this part, but now I can explain it. So if you wanted to have a, I mean like very unique, or let's say a new component, you can always swap with the smart pieces. Like you have smart pieces A, B, C, D, E, F, and G. So you can combine A with G, or you can combine A with F, and also F with G. You can always swap to create a new, I mean, a modular unit. So that's a way you can characterize the component in to create a new one. So that's the answer for the first question.
Thank you. Thank you.
Okay.
Yes, thank you.
So for the second second question, I didn't really like
the
get
second, sorry, my mistake. The second was for Sara, for Sara's presentation.
It's just the most difficult question ever. How can I respond to that? It's, well, I think it's, let's start with that. So when after graduation, I worked with D-Shape, which is a company based in Italy that deals with 3D printing at large scale. So we talked about scale. So there's an issue about scaling up. And I can relate with that. It's so complicated. It's so difficult, and for so many reasons. And also, like, one of the reasons is the time to realize something. Like when you have like not a building unit anymore, but like a neighborhood. And so when you talk about like your city needs restoration, you're, at least to my understanding, you're talking about like, for instance, landscape complexities of bringing stuff there, right? So when I was at D-Shape, we were talking about complexities in a different dimension in terms of, we worked on the Palmyra side too, in terms of bringing awareness to the world about what was happening there and the heritage being damaged there. And so to us, working and like creating, in that specific case, a replica of the arch was a way to initiate a process. And there was a lot of discussion, what can we do after there in Syria? Should we bring one machine, and with that machine, like there was like a lot of speculation around this, right? So that approach at the time was to think about like scaling down the issue. So there was a war context, and we were thinking about how to consider like small building unit using one machine, and with that one machine that allowed all sort of customization, you could fix like case by case, all sort of like different cases of damage. What you're suggesting is again, is very complicated. And I think that we have to put like a system together and to create a specific workflow for that. So can we, what's accessible there? Can we get one machine and then scale down what I want to produce? Can I use smaller machines? There's a whole process to be structured for that specific situation with different ingredients. So yeah, it's very complicated, and I think it's about thinking like, what's the priority? Like, do we need a machine to create that specific outcome? And can we scale up and scale down the outcomes based on what we need to realize? So it's very difficult. I don't have an answer, of course, but I think that this is the approach to start thinking about these aspects. Like,
thank you. Yeah, that's great.
Okay, sorry, I would like to make a question which is in Discord. We have a general question, but maybe it's better to start with the specific one. This is about the post-war Syria presentation, what I consider absolutely interesting. But this is, I have a question for Ziwar. This is from Discord. I have a question from Ziwar al-Nouri and his presentation. What advanced construction methods have you considered to examine the need to build quickly in post-war locations? For example, does the use of DFMA design for manufacturing as a methodology be a viable method to solve these complex problems? Or does the lack of infrastructure in war-torn areas hinder the attempt to use advanced manufacturing and data-centric design development tools? This is from Mariam.
Yes, actually, I mean, like she asked the question, and like actually she replied also. Actually, there is a big lack in the infrastructure there in Syria, and the economical and the resources. For that reason, I mean, like the methodology, I mean, like our main methodology, it was about like how we can find a new intervention. It would be as a power generation for the area which is destroyed. For example, like could be like invest, like it could be like provide the generation for the destroyed area or for the site there, for example, the study site, or could be provide as a shelter or like a structure support, or could be as electricity or as a water generation. So I mean, like for that reason, I mean, like one of the reason why we make this methodology also, it was a big challenge for us, because I mean, we took these things as a post-war disaster city as something it's existing infrastructure, existing like semi-destroyed. For that reason, we didn't take like something it's collapsed on the ground and we want to start from zero. And that was the big challenge for us. And this the methodology to bring from the everything we have it as existing. For that reason, for example, we provide a new material, like we test a new material from the rubble, how we can mix this new like the rubble material to recycle, for example, to bring to make new material, for example, cheap material, let the local community to build it by their own self. Especially, I mean, like we don't have the hand there. I mean, like there is also not just lack in the infrastructure, we have also lack in the people there. I mean, in the handwork there. For that reason, we have to encourage them and motivate them. I mean, like to build it by own self, like by super simply things. Just it will be as a first step to let them like to keep going. I mean, like, and then like start to build their own district. I mean, like our role, I mean, just like to give them the first step, which it would be indirect way to motivate them later. I mean, that's why we took this methodology actually. Yes, that's, I don't know, like if we answer this question.
Okay, great, thanks. And we have another for you, so maybe we can follow with your answers as well. Would you explain the concept behind the muscle shape and diagonal elements in your housing complex design and the material and the system of construction you consider for those elements? Is it for you as well, Ziwar?
It's for us. I didn't get it. Sorry.
Could you explain the concept behind the muscle shape and diagonal elements in your housing complex design and the materials and the system of construction you're considered for those elements?
The muscle shape. You mean like
yeah, I suppose it's the diagonal elements that you show in your presentation and the lesson.
Yeah, like the question, it's what's related of the existing.
Yep, I suppose it's related with the diagonal elements that you build. But yeah, maybe it's yeah. What do you consider is the system of construction for these elements?
Yeah, actually, I mean, like this L system also we provided in this methodology also as the intervention, but also had the same function. I mean, like we let this tree, I mean, like to provide the structure, and the same time, I mean, like inside this tree, I mean, like it would be have the cable to provide for this building as the water and the electricity and the generating this building to make the life. I mean, like we bring this tree as it would be as the heart for this building. At the same time, I mean, like as a function and as a structure to provide it, and the same time, I mean, like to provide a new vision for this building. We bring this idea actually, I mean, like from the courtyard. Why we bring it like as like let's say muscle or curve? I mean, because I mean, like it was about, I mean, like to make something as a contrast between the material and the new things and the old things or the existing thing. Especially also like the building which we have it there, the existing one. It's like it's built it in 20th century, so also it's not have a like it's not a traditional building or heritage building. For that reason, we try like to insert like a new language for this building and to see how could be, for example, the react about this. I mean, the new language, how could be like bring a new things, new vision for the people. Yes.
Yeah. Okay. So. Thanks. Let's move on to a more general question. I think it's a little spicy, this question, but let's see. This is from Yelena Tigusheva, and she asked, this is from YouTube chat. She said, computational design stands for perfection, perfection in design, precision, etc., perfection in production. Most of architects and engineers are obsessive problem solvers. When we see something imperfect, our perception was to figure out what is going on. Maybe this is related with the Neil comment. So we get curious. To start to analyze. We start design. We becoming creative in order to resolve this imperfection, beautiful or works. But being ambitious, professional is never good, perfect enough, and keep developing. Thinking and etc. and it's making objects unique. So she asked, is computational perfection boring? I found it super fun, but I don't know what you think. Maybe Educator can say something about this.
Well, let me answer this question from my point of view. For example, I use in the computational design and parametric design, I all the time say that when we design a deployable structure, we design a motion or movement, because it's different with the conventional architectural. So in my case, I use in the computational design this perfection. I don't say perfection, I say precision, because I need the precision points for create this dynamic at this deployable systems. And for that reason, I think that is very important. So in general, I think that we try to find this balance, not between perfection and imperfection. Of course, the imperfection is very beautiful, but sometimes the computational design have this beautiful too with the perfection thing. So I don't know, maybe depends for every case, but of my viewpoint is these reasons. Thanks.
If I may add something to that. I think there is a little bit of discussion of the meaning as well, because at the end of it, all the computational models that we create are somehow abstractions of what is real. And these abstractions always come with a error, but it is very important to understand the error. If the measurement that we are taking has 1 millimeter of error, creating a computational model for nanometers would be meaningless. So it is always important to take that error bar into account and how much the model that we are creating actually relates to the reality.
Yeah. Maybe I can pick up on that. I think it is interesting that we see like different approaches in design addressed in these 6 presentations. For instance, in the work of Angelica, we see how procedural modeling is addressed, and she's trying to basically formalize and basically explicitly explain how we can work with procedural modeling. And at the same time, maybe in the presentation of Omar and Shervin, we see that this notion of simulation, which I think it is really important to be addressed in computational design session, is really important. And maybe my question is, and when it comes to the simulation and integrating simulation in the computational design workflow, how do you see the role of simulation in general, and how do you see the role of abstraction? Because simulation can be implemented in different for different goals. Like when we apply simulations for parameters such as materials and structure, the way we make our abstract model is totally different than the way we make our abstract model for instance, spatial design, the way we see in the work of Shervin. So maybe you two can reflect on the role of simulation, but I really want to also go back later on to the work of Angelica and this notion of procedural modeling.
Well, I think simulation is helpful, but it's very deceiving. So it's very important to be aware of that idea that not only simulation, but also even optimization sometimes, that you need to be aware of the scope of what you're doing and what you're simulating and how much are you simulating. And this is sometimes a little bit elusive in a sense that we think that if we have simulated something in 1 or 2 algorithms, it is gonna work for sure, and we get overconfident about it. But I think it is very important, especially when this is not my work, but it's about maybe other people's work, so maybe other people can comment on it better. But when we are working with like manufacturing or fabrication, then the importance of the prototyping comes into effect, because at the end of it, that prototyping is the natural process that your design need to incorporate with and work in and function in. So the simulation is important, it's useful, but it has this decisive aspect of it, which we should be very well aware of.
Omar, maybe you can also comment.
Yes, thank you. Yes, for example, in my case, the simulation, well, I need say one clarification in my research. Of course, this project is an academic project, and for this reason, we have with all problems, in this case, for example, the bucket problems, you know. For that reason, maybe is one reason for this. For this is more difficult to build or to fabricate a big deployable structure. But in my research, the simulation and the different simulation, not only digital simulation, of course, is very important, the digital simulation, because it's more fast to design the different geometries and different strategy to design the movement. But it's more easy to find block problems or limit to movement with every structure. So for that reason, it's very important the real simulation, because we need to design much faster different structure. In this case, this simulation in this research is for create more fast different geometries and more precision structures that works in his movement and in his structural and mechanical behavior, of course. But also I say that when we build small prototypes with the 3D printer machines and laser cutting, we build, or we do it a real simulation in a small scale. So this one is a simulation too, because it's not the full scale, it's only a small scale. So this is a very, in deployable structure, of course, from my point of view, this is other type of simulation. It's an analogic simulation, of course, but this small prototypes is very important to create to design the new deployable designs.
Great.
Thank you.
If I can just quickly comment on this question as well. I'm not sure I can talk about perfection. I think I cannot, but in relation to curiosity, I think it really depends. Like, I think computational design can in fact not be at all curious or interesting very easily, especially when done in practice. And I've experienced this many times because of how restrictive time, money, resources, everything can be. It just becomes some process where you're essentially kind of convincing yourself of what you already know. But but it can also foster creativity and curiosity by doing a very simple step, but very brave step, I think. Just abandoning every objective. So like we've seen a few projects here, for example, and in general, most computational design projects, there's always an objective, there's always a goal. And of course, there needs to be a hierarchy goal, like we want to achieve something within this design, but the smaller objectives of optimization and fitness and these ideas, I think those are the biggest bottlenecks to curiosity. And we haven't had a way to take them out yet, because it just became something random, right? Something random that doesn't really generate something useful. But I feel slowly there are fields around us that are developing theory and research on how to do that. And I would point my finger towards there, or of how can you design without objectives? I think this is kind of like a very big question for me personally, and maybe for the field in the future. I don't know.
Can I just throw something in there also? I mean, the question about is perfection boring? I mean, that's an interesting one, because I think in a way, one of the Achilles heels for architects is they think that something that's visually complex is going to be interesting. And to my mind, a simple kind of processing script that can produce a kind of like the stuff that Roland does so well, Roland Snooks, it's actually quite straightforward. But if you take something that's formally quite simple, like the soap bubble, I mean, if you just kind of like blow a soap bubble, it's as a boring sphere, but it's actually way more complex in terms of its material behaviors. You know, I think we have, as architects, we're always looking for visual complexity because we think that kind of formal complexity is boring, but actually it's not necessarily the case.
Yeah. And anyway, I think that with this, for me, more fun about computational design and about to make complex things with simple actions, for me, which is more fun, is that you don't know the result. If you already know the result, you don't want to go all over all this procedure, because why are you going to do all this procedure if you already know the result? The idea is to push it on to the unknown. That's why I was reading this Sean Fraser book or in his lecture, he say always that there is something blind that you don't know. the final result. You can figure out the rules, you can figure out the elements that you are going to use, for example, but you don't know the result. And this is what is more interesting. And this is what is more interesting about architecture as well, that you never know what is going to happen with your building. You never know what's going to be the final result. You just have an idea and you project this idea to the future, and then you see what is the real result. Maybe this idea of simulation as an idea that we can control the future, it's a little bit weird, because finally we don't know. Maybe we can expect something, but finally, we never know. Even in this second question about how do we think that the digital design in the context of COVID, and today our future changed already. Now we are all of us are digital, even our classes are all digital right now. And we didn't expect it that we know that it will happen, but not so fast and in this way, how is now happening. So maybe it's, at least for me, that's why for me computational design is so fun, and that's why I do it all the time, because the idea of that complexity, nothing born complex in a way. You start to build the complexity with simple steps. That's why it's so easy to teach it as well. But maybe I can introduce this other question from the audience. I don't want to let anybody out. So this is, okay, this is related to what I was saying. What do you think about the applicability of computational design? It's a general question. In the era of COVID or post-COVID worldwide, economical labor crisis and escape of city population. The country for most, the escape of city population to the country for more spacious and sustainable living. Maybe this is related with Rem Koolhaas's last book. I don't know, it's mainstream in a way. Can we, on a planet scale, afford these expensive computer-generated structures, or what do we need them? This is one question, and the other is a little bit different. So maybe we can start with this. It's a complex question. Have you been thinking about this?
Well, let me answer the question. For example, when I read I read this question before in YouTube, and I remember I defend my PhD thesis the last week, and when this pandemic time started in the last in the past March and April, I remember here, for example, in Spain, maybe you see in the news, was very dramatic times, because was very difficult times, and I remember seeing the news and the TV news. I see how the military people or different companies start to build or to assembling and temporary hospitals, and I remember how during more or less 2 days or 3 days in assembling and create this structure. Okay, when you see my presentation, we can say that it's very obvious to the emergency architectural application. So I believe that this structure have very generous qualification, like it's very faster to assembling. It's we only need move the structure, because the structure have an assembling process not in the moment. So I believe that the deployable structure or the kinetic in general, the kinetic structure had very interesting application in the conventional architectural, and from SMiA research group believe that and we try to make very good forces and very good application in the academic projects for create different options to apply this project, this deployable structure or this kinetic structure, and focuses in applied in emergency architecture. Maybe we had very good possibilities to apply in this.
Okay, that's great. We have another question from the YouTube chat. Is from Elena Tugushev as well. What do you think about, this is a general question to everybody, what do you think about educational challenge in teaching computational design? Many students shows that computer science students have trouble learning to think and express themselves computationally, when architectural students have serious misconceptions about how computer programs works and overall workflow would create a poor student design performance. So she said, hot design mess without any practicality, meaning they can't repeat steps after the instructor, but they cannot think or create independently. Maybe it can be related with something that Angelica shows in the, and Gonzalo in their presentation. What do you think?
Gonzalo,
even everybody can take it, but I think maybe it's
Sure.
related with something that you said.
Yeah, I just wanted to mention something. I don't think that it's difficult to teach the new generations computational design, but I think that it's important to teach them, as well as the technique, also the computational thinking, in order to push the theoretical part and the practical part at the same time. It's not one or the other, but the two parts doing a whole process of creation. So in that sense, for me and for our course, it wasn't that complicated, because they could understand the technical process of computing some step through the computational thinking theory that it was that we were teaching at the same time. So in that sense, I think that it's important to keep these two together. And I think that the new generations, they're like very open and open-minded to incorporate that, especially when you explain also the benefit of the digital process, not only the computational design, but as well the fabrication design. So in that sense, when you explain that you will save money, resources, time, that you can rationalize the geometry, etc., to mention some of them, they start thinking about a more realistic application of these new techniques and logics. If that answered more or less the question.
Yeah, I think in the way, yeah, just continue, yeah.
Sorry. Yeah, I also have a feeling about it. I kind of had the same feeling before we started this kind of brand new experiment about how to teach architecture or designing modeling through our computers, but I actually found this as a brand new opportunity to fix a lot of things that were kind of missing in the before times of COVID situation, because architecture schools usually has this branch between how to teach architecture in a way that you can really feel it, you can really touch it, you can really model it with your hands, and you can learn about these creative processes. But it has already a branch between a professor that doesn't really manage any digital tools, but the students already need to feel this knowledge that they really need to learn how to use these digital modeling tools, because they had to work on it afterwards. So I really think that this experiment that we had bring to us some brand new tools, as simpler as sharing your screen with your professor and modeling like together something. Like really the opportunity to send a file, to share the file, to change it from a program to another one, and to be able to be a companion with the student in the process that they have usually alone with his computer. So I think that it was really nice. It was a really brand new opportunity, and I really think that it has a lot of challenges in the future, but it's also fixed a lot of problems that we had in the past.
Yes, it's also true that sometimes we just bring, I mean, not particularly in my case, I have a critical point of view about to stay all the processes in a black box that you don't know, because in a way you can control some parts, and it's impossible not to think that the software that we use and the plugins are designed by other person. It's not designed by a machine, it's designed by a person. It has a bias, it has a context, no, where they develop the softwares that we use. And sometimes it can be a little bit dangerous if we bring to a student a black box that that the student doesn't know how to where these belong or how to control it in a certain way. So we are maybe this theoretical approach to computational design can be a way to study maybe the history of the softwares or where they come from, where they belong, in which context they will made, or something like that can make us be more critical about the tools that we use, not only as a tool, more important as a way to think and to design as well. So maybe it's just a comment about it.
Can I say something about this question? I totally agree with the two professors, and also I have my opinion that because I'm teaching recently with Satoru in one workshop, and I think from two perspectives. When I was studying, I have this question when I first started in at the Bartlett, because we actually started to doing research by play with the Rubik's Cube. And at that point, we don't understand why we need to start with a single cube. But the most interesting part, it's an open-ended generative system that you kind of need to add one rule on the top of a new rule on the previous design system, and then you can push your design to another stage or level. If you think the traditional way we do design for us architects is kind of like a top-down design method, and this way is kind of like a bottom-up. If you don't, you couldn't let yourself be controlled by all the parametric tools, but you can kind of combine the two different design methods, I mean the top-down and the bottom-up, and you can fix a kind of purpose why you are doing this and use all the algorithms as a tool. But actually, it's still human beings that we architects decide which kind of form we finally use. So it kind of combines the configurations or algorithm with intuition. It's a combination. So when we play with the new tools, new algorithm, it kind of, we have more possibilities to do design, and which is a very good thing, I think.
Yeah, that's great. Yeah.
maybe what I want to say actually addresses everything that has been mentioned and ties it back to the notion of scale that Neil was mentioning at the beginning. Because I think if you take into account that computational design is a different paradigm, we need to acknowledge the fact that the possibility of space that it provides is different to conventional design as well, meaning that certain things that is easy in conventional design, it's super hard in computational, and vice versa. And this, like getting used to this is crucial for students to start learning computational design, because when you get used to this, then you develop that intuition that has been aforementioned, and then with that intuition you can continue. And I want to tie it back to the notion of scale, because that is one of the things that is lost in the computational design mentality or paradigm, because we are so used to zooming in and zooming out and scaling up and scaling down, that we lose that notion, that we lose that intuition, in the sense that we can't relate to actually how hard is copying 100,000 cubes just beside each other in reality. And I think acknowledging these limitations and these differences between these two paradigms is very important, not only in the education, but also in the practice, to be able to apply them to reality.
Okay, maybe I can introduce another question from the audience. maybe one of the last. But anyway, I encourage you to continue this debate, this discussion, our conversation on Discord in our channel, Digital Design, and Computer Design, sorry, because I think that we can continue talking about this for longer. Even we have another session next Saturday about the same topic. So, okay, Abida Mikati. Hello, really incredible and inspiring work. Thanks Reparametrize group for sharing this new methodology of work. Really, you inspire me taking this under consideration after the disaster of Beirut. Till today, all the work of the reconstruction is so far about anything related with 3D scanning or smart building. From the first day after the crisis in Beirut, we tried to create the best methodology for reconstruction, especially with the high number of heritage buildings in Beirut. So my question is, what is the first step that is most taken under consideration when we use an AI in our methodology of work? Is for Ziwar.
Yes.
Yeah. Okay.
Yeah, actually, I mean, like this question, it's nice also because I mean, like we are looking, I mean, like now in the future, the near future, I mean, like to have a recoding post-war Lebanon, especially also Bilal, he's from Beirut, and also like we are looking to start to make this research, I mean, like and apply some methodology in Lebanon. And especially, I mean, like the methodology of this research would be, I mean, like a change according to the function of the building and according to the function of the site and how much the importance of this building. For example, I mean, the heritage, I mean, like when we were talking about in our research about like the residential building and the mixed use building, it was about like something it's built in the 20th century. As we said, it's not like heritage or history building, but we did also like as an example for old hammam. I mean, like it was in the area, in the district which we had it. And we did also 3D scanning for this area. And the most important things, I mean, like when we start, I mean, like we consider a lot in detail, I mean, like how we want to 3D scanning this heritage building, because it's totally different if you want to 3D scanning a residential or heritage, because the heritage, we are looking to like refix it, let's say, or like make it like in the same way. Could be, I mean, like according to the code of the building there or according to the rules of the area. For that reason, I mean, like what we have to consider first, I mean, like the rules and the code building there, I mean, and the parameter, what we have to see, I mean, there in the area, how much we have to change, how much we can integrate this intervention. And according to that, I mean, we will consider it in the point cloud and the data which we want to collect it. And anyway, also like that's maybe the answer would be long, but also like could be maybe like we share maybe our website. She can contact us also, like if she's looking to work in also like for her things about rebuilding or like working on the heritage building in Lebanon. Also, we can share with her also our thought and what we had also like so far. Maybe like it's because now briefly I want to say it.
Okay, that's great. Okay, we have some specific question that I think that maybe can be answered on the chat or maybe can be part of a discussion more specific on Discord, just to maintain everything on time, because maybe it can be this a little bit long. So I would like to offer to the committee and the speaker now maybe you have a final comments about the session today. Maybe you want something to add. This is the moment to do it. I have mine, but I'm going to let it to the end so you can speak freely with time now. Okay.
I just want to say, I think it's just great that we have these presentations today from people working on Syria to people coming from Chile, literally bringing the world together. It's just something very novel and something very special. So I just want to thank you guys for your contribution. Super fascinating.
Well, I want to say for me it was very great opportunity to share my research, and I'm very happy to do that. And I only say you thank you for all Digital Future teams. Very thank you for giving me this opportunity, and very thank you for this discussion time, because it's very, very interesting, and I learning all the time about the different computational design things. So thank you so much.
Maybe I just want to say one thing. That is, we had something like 6,500 people watching on Bilibili in China today at some point. We still don't have enough of a Western audience, so please spread the word, because I mean, this is a kind of revolution its own kind of way, and I want people to benefit from this. So thank you.
Yeah, I think there are a lot of opportunities in East and Middle East also. So maybe this is also saying that maybe West is a bit oversaturated, and we have to change that. And I also really like the presentation. I would like to congratulate everyone. I think when all these three computational design sessions come next to each other, I think it would be a very good reference because I think most of the topics in these 18th presentations will be covered, and I'm really looking forward to see how this will fold up later.
Okay, and I don't know if there are another final comment on the committee or the speakers.
I just wanted to invite everyone again, because we've talked about it before, but just shout out to everyone. Thank you. It was really great. And as Marina said, maybe we can continue the discussion on Discord. That is also a great opportunity to share your thoughts and discuss with others. So there's a whole crowd of younger people interested in these topics, and we try to provide a platform for everyone to discuss that and talk about also sharing, learning these resources. So yeah, if you have time, join us.
Yeah, I think this picture it's really important. I'm really sorry for some questions that we left without read, but I think it's important that you, the rest of the speakers and the part of the audience that were today, to share your other questions and comments. I think this is super important to maintain this level of discussion that we have today. So I want to invite you for the next Saturday at the same time. We are going to have the next session of computational design. Sina Mustafa is going to be hosting the next presentations. So I'm really happy to see how this continue going. And keep in mind that we will open the call for robotic fabrication presentation as well. So I would like to have more presentation and more discussion here and conversation between us. So thank you, all of you, for please, Neil. See.
Two Saturdays time, we have a special session on the future of education, and I think this is incredible. It's slightly off topic, but absolutely super important given the discussions about COVID and so on and so on. So the 12th of September, we have Sanjay Sama, who is in fact who leads open learning at MIT. He's going to be talking, and we're going to have a group discussion, a panel discussion about that. So it's slightly off topic, but super interesting.
Yeah, and we'll hope that all the educators that we have today, young educators, can be there and making questions and participating as well to this talk. So yeah, great, Neil. Thank you.
Thank you.
Okay, thank you all of you. It was incredible. See you next Saturday.
Bye-bye.
Bye. Bye.
Thank you.
Adios.
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 Ciao, Marina.